Hi, welcome everybody. Today's MLR Open Design discussion. Today we have a presentation by Pedro Ciambra on the representing data flow with MLIR.
Right. Jack, thank you very much for the invitation. Today, I am a first-year PhD student at doing a co-tutorial between Unicamp Brazil and INSAREN here in France. And today I'm going to talk about my master's work that I did back in Unicamp during COVID, during the last 3 years. So I decided to separate my presentation into two parts. First part is going to be just an overview over my work, same structure as it would be in my defense. And second part, I'm going to go a little bit more in depth about my use of MLIR, the challenges I had, the solutions I found. And if we have time, I had a little proposal to make, and I wanted to see your opinion on it. But as I said, I'm going to try to be quick, so we have time for discussion after the meeting. So let's go. Okay. So part one, it's my work, my master's work. It is a compiler for Dataflow that is written within MLIR. Dataflow, I'm going to go over the basics here, as I expect not everybody is going to know very in depth. It is a very mature research subject. It's exists since the 60s, and it has been a very successful approach for especially for the more application-specific parts of many different subjects, such as real-time systems, reactive systems, hardware synthesis, things like that. And now it's having a resurgence with machine learning, which is a specific application of Dataflow. And because of this very heterogeneous landscape, there are many different models of computation in the family that is Dataflow. And each of them have different abstractions, different constraints, different naming conventions, and they are all very much built for purpose. And because of that, the tools that already exist nowadays weren't really built with intercompatibility in mind. Even though there is a lot of overlap between the different areas and lots of things that could potentially be reused between them, but currently are not. So the original thought was that MLIR is perfect for this application because MLIR was made with this compatibility and reusing in mind, right? So the objectives here is to enable Dataflow researchers to access state-of-the-art compilers more easily, especially especially in things like polyhedral compilation and hardware design, such as circuit, etc. Also to facilitate collaboration and integration of projects. Several different Dataflow languages were proposed, but I don't think many of them are widely accepted as an interchange, commonly accepted interchange language. Making the advantages of Dataflow more accessible to other communities, including the compilation community. There are advantages to using Dataflow that aren't really used a lot in other areas. And enable reusing of components, such as implementations for actors, that is specific optimized function implementations, schedulers, runtimes, optimizations, etc. For that, I needed to tackle this problem, which is what exactly are the requirements for a Dataflow format that is useful within MLIR's constraints? Like this, what exactly can I do with the tools that MLIR gives me that will be the most flexible and most useful possible. Just going over it really fast, Dataflow is when you're programming in Dataflow, you're modeling your algorithm as a directed graph, such as this, where each vertex of the actor, each node, represents an atomic computation. So it just consumes data from input ports and inserts them into output ports. And this data exists as discrete tokens of fixed size. And these tokens live in a first in, first out data structure in between the executions between the different actors. When you design your algorithm like this, the data dependencies are explicit, and it's very easy to find the inherent parallelism of your program. So it's good for writing multi-core schedules and for generating hardware description language. It's also using networking and many other applications. Just noting that this graph is not necessarily acyclic. Feedback loops are allowed, and when they exist, they usually need some initiation tokens here, so that the actor can execute for the first time without being starved of data. This is going to be important later in the talk. So as I said, there are many models of computation in the Dataflow family, and they're usually separated into three main groups: static, dynamic, and quasi-static. They go from more strict to more relaxed, and usually the more strict you are, the easier it is to guarantee some things at compile time, such as finding an efficient schedule or trying to minimize memory or things like that. But it gets more and more less and less expressive. So there are some algorithms that are not easy to express in the static model. So we're going to go through them from more strict to less strict. This is just so you guys can understand exactly what I'm trying to model with MLIR. First, we have Synchronous Dataflow. This is the most constrained model. In this model, whenever you execute an actor or you fire an actor, you always consume and produce exactly the same amounts of tokens, exactly the same amount of data. This way, you can detect if your graph is admissible, which means it won't lead to deadlocks or starvation of any actors, and you can generate a schedule statically. And there has been a lot of research on how to efficiently schedule a graph like this. Going up in flexibility, we have Cyclo-static Dataflow, where even maybe the rates are not always the same, but they are cyclic and predictable. It's useful, for instance, if you're working on an encoder decoder, and you know that the shape of the data that you're consuming is consistent. It's better to use this model instead. It can, in general, be converted back into a synchronous Dataflow, so it's still totally static. Working with that, then we get into parameterized and interface, which are extensions of Dataflow so far that allow for hierarchical graphs, where an actor can actually be just a reference to a smaller graph that improves reuse and gives you more flexibility when you're designing your algorithm. And you have access to parameters. Parameters are, in this context, are not counted as inputs. They are more akin to templates in programming. So these are statically known values that they're going to be used as inputs for the scheduler. So the data rates for your actors may depend on these values. You can use this for one second. Sometimes you want to write an algorithm that's adaptable in the sense that sometimes in known times these parameters can change, and in that case that it goes into the subset of quasi-static models where you change between different modes of execution, and when it's time to change your parameter, you reschedule all of the static part. This can be used, for instance, if you were writing a image processing algorithm and you want it to be able to work with many different sizes of images. You would provide the size of the image as a parameter, and the algorithm will reschedule itself as needed. And then at the topmost level, we have dynamic models of computation, such as Dataflow process networks and count process networks. And these are, in these, the behavior of the actor depends on the actual value at runtime of the tokens that it reads. So this makes it much more unpredictable. There are also many different types of restrictions you can put on the activation rules for these actors. But in general, they are Turing complete. And so you need some kind of runtime to manage memory and scheduling. So it's much more flexible, but also more expensive in terms of resources. Just a note on terminology. In the literature, we usually say the nodes referred to as actors, but I find that this is a little bit ambiguous when it's talking about an actual node of the graph, or when it's talking to its implementation. Obviously, you can have more than one node refer to the same be implemented by the same function. And so in my work, I make this distinction when I'm talking to a node of the graph or the implementation. Some works mix the two and represents both implementation and the coordination code in the same place. But other works have this very strict separation between the graph and the implementation. So just to get that clear. Talking a little bit now about related works for my work. As I said before, there are lots of works in Dataflow, so I'm just gonna talk about the two that are more that I actually use in my work. First is Prism. It's a Dataflow IDE written based on Eclipse. It generates multicore C, and it has a graphical interface for designing your Dataflow algorithm. So it has a lot of work put on it. It has state-of-the-art optimizations, and it saves this graph in a custom XML format that is declarative. It's basically an XML format that describes the actual each element of the graph that you're creating. And then you have a diff, Dataflow interchange format. It's somewhat of an older project. It's part of a Java-based library for Dataflow. It's simple. It's human readable. As you can see here, there's not much complexity to it. There are no assumptions about the mode of computation. It's supposed to be quote unquote universal. and it allows arbitrary informations as custom attributes. So it's like to think of it of kind of like a JSON of Dataflow. And so we finally arrived at my project, which is just a simple single core static Dataflow compiler written in MLIR as a proof of concept. So what the main thing that I do is that I read a source graph in diff. I parse that into my own dialect inside of MLIR. I do all of the scheduling and generate all of the buffers for the edges of the graph using standard techniques. Nothing new here. And generate LLVMIR, which consists of just the buffer allocation and a list of function calls, which makes up the schedule. That gets linked against the implementation for the actors, which in the test that I did, they are implemented in C, but they could potentially be written in anything that is compatible with C, with C functional, C FFI. Could be written in Rust or in C++, potentially. So far, there's nothing new here. This is just there is no novelty here. But then, if we actually start using the MLIR for what was intended, which is mixing representations together, right? So if you raise the C code of the kernels into polygeist, into MLIR, using polygeist as a front end. So I'm just transforming the C code into SIF, which is like just simple structured code. Then I suddenly have access to some information that we didn't have before, which is information about how the graph is structured and how the kernel is actually being used. So as a demonstration, we created this dead code elimination pass that can take a part of the kernel and just remove it if you're not using the output. Like for instance, this is a very simple example, but if you're interested in calculating the magnitudes of a vector, and you happen to have this implementation for Cartesian coordinate to polar coordinate function available to you, you can feed that into my compiler, and it will automatically detect all of the operations that flow exclusively into the unused output, in this case the angle, and it will just remove it from the function, since we don't need to use it, and save on cycles and save on the memory that would be necessary to keep this information available. And so with this done, we compared against some existing applications that were available in the Prism project. We compared with against Prism's single core performance, since I did not implement a multi-core scheduler. We get comparable results, except for very large graphs, so where the optimizations that were implemented by Prism make a lot of difference. I'll go through the results real fast. First, I have this simple implementation of an algorithm that takes a color video and outputs a grayscale video. This application I developed specifically to demonstrate DCE. So Prism originally does not support unused outputs. So what I did is, in the Prism implementation, I did the naive solution, which would be to create a node that just consumes these two and don't do anything with it. So what I do, what the algorithm is just read a frame of video in RGB. So red byte, green byte, blue byte. Transforms that into HSL using the basic algorithm. HSL is hue, saturation, luminance. Discards the two and just takes the luminance and converts that back into RGB. Comparing the results, we have Prism as a reference. Even without the dead code elimination pass, we get comparable speed, but just half as much memory because we don't because my scheduler is smart about the way it allocates memory for unused outputs. And with that code elimination, we get use only 1/3 of the memory and get 50% better performance. So, okay, this is an application that was tailored specifically for this optimization, but I think it demonstrates that this is useful. The other applications we tested against are stock. I didn't do any modification from the originals in the Prism project. Here you have a subtle filter, very simple, 3 nodes. So a monolithic actor that just takes a frame of video and outputs the version with the subtle filter applied. And as you can see, the schedule is trivial, so you get basically the same performance. There is not much freedom here in the scheduling, so just to show that like it works very well. And then we have SIFT, like scale-invariant Fourier transform. Sorry, it's this is covering the title for me. A feature transform, sorry. And this is much bigger algorithm, has several hierarchical layers, 57 nodes in total. This is just for the actor code, so ignoring the coordination code. It's more than 5,000 lines of code, and in this case we do badly. It only gets about half the performance, but we use 4 times our memory. And this is because I simply couldn't compete with all the optimizations that were done in Prism, particularly the broadcast nodes that are basically optimized out in Prism, which makes sense because a lot of people put a lot of work in Prism so far. So I'm not that sad about this. And so this was part 1, which was my work itself. I'm gonna ask anyone has questions about this so far, because part 2 is going to be very technical about MLIR itself and my strategies and how I'm using it. So you can, I think, ask for attention. If not, I'm just going to continue. So I'm talking about the requirements that I was trying to fit, the approach that I had, the solution I found, and then open a bit for discussion, if we have time. Yeah. Okay, so considering the description languages that I had to work with so far, we had diff, which was basically exactly the same. This, right? A list of nodes and a list of edges, and a list of interfaces that have the extra informations for that, such as the types of the ports, the names of the ports, the rates that each port consume and produce tokens, etc. And this is very declarative, right? This is not very SSA-like, in the sense that we're connecting the outputs, the inputs of operations into the outputs of other operations, and representing the graph using MLIR, right? We're representing the graph in a more abstract way. So the good thing is that we're very flexible, right? We can just define operations for any kind of abstraction. But the bad part is that we can't use MLIR's type system the way it was intended to be used, right? So my first approach was having two dialects. One that has this shape, where I have a list of nodes, list of edges, and another that conforms to MLIR's SSA nature, where I don't actually have operations for edges. I'm just using values to represent the ports of my nodes. So I'm going to go into detail. Don't worry. One of my main objectives is to keep the IR human readable. This is important. I want to keep the interface recognizable so that if I have a bug, for instance, a type mismatch between two ports, I want the port to be immediately recognizable. I want to know what node I'm having a problem with, and what's the name of the port that I'm having a problem with. So I don't want name mangling. I don't want parameter indexing, which is referring to parameters and ports by their index instead of by their name. And this will be clear shortly. Here we have, as an example, my declarative dialect for that algorithm that we were talking about before. So this is what it looks like. I have a graph operation that contains the topology of my graph, and that just contains a list of kernels. In this case, it's just the C interfaces for the functions I'm calling, list of nodes that just have the references to the kernels I'm calling. You can have like a one-to-many relationship here, and a list of edges, which are just the relation, just the producer node, producer port, consumer node, consumer port. Edges can have edges need to be operations in this case, because edges can have extra information attached to them. For instance, those delays in the case of feedback edges, as I've talked before. I've also implemented a functionality of default parameters, where in the graph level, I can define name value pairs, and if any kernels define this parameter but don't define a value, they can fall back to the value of the default value defined in the graph, or in the case of nested graphs, it can like just go above in the hierarchy of MLIR operations to find the correct value. So similar to symbol resolution, but since I'm using attributes instead of actual operations, I couldn't just use the built-in MLIR symbol tables. One thing that I should note here is that even though I have like custom attributes for parameters and for ports, parameters are just name value pair, but ports are triples: name, type, and rate. And this rate, in the case of static data flow, is just an integer, but it could have any arbitrary information here for more dynamic models of computation. So this could be a list of integers. This could have this could possibly be a reference to another port, and so on and so forth. In the case, for instance, in the case of Boolean data flow, which is one of the dynamic forms of data flow, you can have one port being turned on or off based on the state of another port. So this is the kind of flexibility that I need here. You can see that I'm pre-computing the value for this rate. In the ideal thing would be to actually have this be a value that I'm computing using actual arithmetic operations and defining the parameters as operations as well, so that I didn't have to do this like this. But it was pretty low on my priority list when I was first implementing this, so I just left this for future work. But the idea is that in the future this would be just be resolved by constant expansion instead of just having it hardwired into the IR. Going on. And then the idea was that I would take this high-level dialect and convert that into something that looks a little bit more like the SSA type of dialect that is more, I guess, that makes more sense in MLIR, so that I could use the automated type checking of MLIR and the pattern matching infrastructure and things like that. So the ideal in my mind, the ideal dialect would look a little bit like this. You would have a node with a name, reference to implementation, etc. And instead of having the ports defined as attributes, the ports would be defined as the parameters for the input ports and as the result values for the output ports. And then I could, instead of having an explicit edge operation, I could just use these values as references, as references to the actual ports, and like would make sense, right? MLIR doesn't require you to have a cyclic graph, so this could work even with feedback loops and etc. But the problem with this, like one of the issues, is that between different MLIR passes, it's not guaranteed that we have that we keep the names for the operations, right? And so if we do an optimization pass, at some point the information of the name of the part that we're referring to will be lost, and it will make debugging more complicated, right? It hurts the legibility of the representation. And also, because now we don't have edges anymore, all of the extra information about the edge needs to be encoded inside of the type of the value we were using. So, for instance, if this has an output port that has rate 100, then we need the rates to be like some kind of parametric type. That's okay. That encodes the type of the token and the rate. And as we said before, the rate can be arbitrarily complicated. Like the rate needs to be able to contain maybe a list of maybe a thousand different values for cyclo-static data flow, or maybe it needs to have a reference to another one of the parts of the actor, or etc. And doing all of that in terms of types seem to me like it would take a lot of work, and in the end wouldn't be really. I mean, it feels like a workaround, right? It doesn't feel very natural to represent edge information like that. And so one way of maybe avoiding that would be to represent this information as parameter indexing, right? Maybe instead of having the names of, maybe we allow the name of the port to be lost, and you only refer to the ports as their index, right? The first input port, the second input port, etc. And then we store those indices as part of the type information if you need to refer to them. Again, I was hesitant to do parameter indexing because you lose debugging information that way. And also, if in the original source code the type checking, the actual type coupling you have is in the line of code where the edge is defined, now you lose that, because now you need to put that information inside of the node, inside of the operation that encodes the node. And so if you have an error, it's the nodes that will be flagged as the source of the problem and not the edge. And so all of this is like thinking forward into imagining a compiler that's very easy to use and has a lot of friendly tools instead of just machine code.
So perhaps a question here, like,
okay.
So in this example, for example, you're not showing locations, right?
Oh yeah, I'm assuming that all of the source code or source code information is kept, right, in MLIR. Yeah. So I'm each transformation still keeps the information of the original source code, right?
So yeah. So I think my question here is like, with respect to the information about the edges, I mean, it seems like if we use the fuse location for these nodes consisting of this, we should still be able to preserve this information, right?
Yes, you would. I was getting into that. Yeah.
Okay, sorry.
That's no. Yeah. The point is, like, all of these problems have workarounds, right? It's not impossible to represent everything that I want in MLIR. The point is that all of these workarounds build up on themselves, right? At some point, it looks like this dialect is just like a pile of workarounds and hacks just to make the dialect kind of look like what I wanted it to look like. So in the end, I thought, okay, this isn't going anywhere. The benefits of using MLIR's built-in type checking and pattern matching is not worth all of these like contortionism to make the Dataflow data look like MLIR graph, right? So that's the decision that I arrived in. So in the end, I gave up. I just use my declarative IR directly, the one that has the edge operations. And I decided to do the type checking manually. So I was very lucky because I'm doing SDF. So I already needed to walk the graph and pass by all of the edges to check if the rates were consistent. So I just plugged my type checking in there. But as I said, like this is not general, right? This only applies to SDF. This makes my dialect not suitable for modes of computation that need more complex information about the edges. So ideally, we should find a way to encode more information in the outputs of operations or something like that. But the way that the MLIR looks like today, I couldn't find a solution that I was happy with. And so, as a note, we were talking about this in the LVM discourse. Lustre, which is another Dataflow project, has its own MLIR dialect, but it has a very different philosophy than what I'm working with. This is one of the projects that mix the implementation details with the coordination code, which is like the data flow topology and rates and things like that. And so this also wouldn't be very compatible with what I'm trying to do. And I'm trying to do the most general thing possible so that we can finally start reusing some schedulers, things like that. So that is, I ultimately failed on this objective, which is to find a common language for all Dataflow applications. So this is the main thing I wanted to say, and that's why I structured my presentation like this. I wanted to ask you guys for your opinions and your feedback on what I should have done, what you have tried, and if a dialect such as that would be useful for you.
Actually, Pedro,
yes.
I missed the discussion on discourse. I'm sorry. Maybe that was discussed already, but I'm not following why you think the Lust philosophy is so radically different, especially given that in MLIR you can use regions to encode those actor implementations separately from the graph. So why do you see that as a big departure from what you are interested in?
It's a big departure because I'm not really thinking about designing your. I'm thinking that somebody else will design your actor implementations for you, like some expert that knows very much about the target application, and somebody else that will write a very good C function that implements your code.
Right? Can't you just call a function that captures this implementation in a separate module?
Exactly. I'm trying to build a converter, like an adapter between a C foreign function interface and the format that looks like a Dataflow actor, right?
Oh, okay. So you don't want to force the actor to use MLIR even at all. So it could be something else.
Yes, exactly.
Okay. I still think that can be done in a more. I mean, ideally, I would try to look for more like tighter integration with the Lust dialect that you're implicitly referring to. But I understand it may not be easy, but I don't think that this kind of actor implementation issue is really the biggest problem here. But I'll be glad to discuss it offline as well. So.
Yeah, I've had a very illuminated talk with Dimitro, and like the main thing that came from that.
Oh, he's here.
Oh yeah. Hi. The main thing that came from that is that, like, really, it's a very different philosophy from what I was thinking about when I was in the masters and doing this work.
Yeah, that's right. But in terms of modeling, especially given your goals to integrate more tightly with the type system, with SSA, etc., it seems like you're going to most likely go through very similar design questions. So, but we can discuss that offline.
Definitely. Yeah. So, sorry, have you been counting how much time has been passed? Sorry, I
mean, roughly 45 minutes.
Okay. Thank you. So I wanted to finish by giving a small proposal about MLIR syntax and feature. I don't expect this to be like this. This wouldn't solve all my problems. but it would make me a little bit more, would make me feel better about doing some of those workarounds that I was talking about before. This one is basically named outputs. Maybe in the definition of an operation, we could give names to all of the outputs that operation defines, and we could refer to those values by the name of the operation and that actual name, instead of just by the fragile name, right? That the temporary name that is assigned to it by MLIR. I don't think I don't know very much about the internals of MLIR and the actual internal representation. Like this when I started doing this this compiler, I have never messed with LLVM before, never used MLIR before. So I'm not sure if this makes sense or if there's an obvious way to do this that would make this unnecessary. But I think this would be useful in more than one situation, like, because this is like basically a member access, maybe member access implementation, which would make sense in something like a general purpose programming language. Like every programming language has structs, right? So this is a kind of feature that I very much missed, and I wanted to, yeah, and it would be useful for me to represent the outputs of factors. So this is another thing that I wanted to ask your opinion about. And well, for my presentation, that's it. Originally this presentation took 20 minutes, but after some feedback, it grew to this size. I expected originally to have much more time for discussion, but the time is now. So.
Can you go back to the previous slide perhaps for a quick second?
Yeah.
So with respect to like the names and the types, so this would mean now is the case where the names now are load bearing. So you know, with respect to type checking, right?
Yes.
What would names and the type mean?
Yeah, the name would be part of the signature of the operation, right? It would be stored in the same place that stores what are the types of the inputs and outputs of the operation. It would be optional, right? You could still use this syntax, but if you use this syntax, it would keep, and you wouldn't be transformed through different transformations, right? It wouldn't be regenerated in the same way that this kind of
questions like this. So on the consumer side, other op, what is other op's signature? What's the allowable types of other op?
It just takes. I'm assuming that they have the correct. Like it takes I32, I32, or I'm assuming it's these two are equivalent, right? These two lines are equivalent to these two lines.
So, but I think then what you're saying is like the names do not actually interop with the type checking. So all the behavior with respect to type checking calls, names is syntactic sugar here that you just want preserved rather than being load bearing in the type and semantic checking.
Yes. Well, if I try to index this with a C or another name that is not defined by the operation, it wouldn't work, right? But
I'm gonna beat a slightly dead horse here and say the usual line that MLIR is not a programming language.
Yeah.
Right? It is an IR, and so having this kind of I mean, even LLVM there were some issues with the SSA names had to be preserved, and MLIR, the choice was made to just, you can have an interface that changes how the op prints the SSA names, but this is like, these are not preserved and they're not guaranteed to be, one or the other if you have multiple ops use the same name. and also just there's no like dot syntax going on. So yeah.
Oh yeah, I just saw, but on the other hand, there are a lot of like programming language like abstractions in MLIR, right? Like it keeps the abstraction that is like passing in parameters as a list of values, right? Which is something that we
none of those programming language like abstractions, I mean, people write them by hand, but then you have to accept that you're writing an IR and not a programming language. So
maybe,
for example, PDL has a front end. Some people write their own Python front ends to it. IRDL, I think, also has a front end. I could be wrong, but at least if it doesn't, it plans to have one. So most of these dialects are in reality a close modeling of a hypothetical or real front end to it. Writing IR by hand is not exactly supposed to be an enjoyable programming experience.
Yes, well, but that makes sense. On the other hand, I wanted this IR to be like as easy to adopt as possible by the Dataflow community. So I wanted the structure of the IR to match as much as possible the structure of the Dataflow algorithm, right? And in Dataflow, the order of the outputs doesn't matter. What matters is the name, right? So this is something I missed. But I understand what you mean. At some point you need to like accept that only computer is going to read this. So what it looks like textually doesn't matter.
No, I think Jeff. Well, I mean, I may be projecting, but like I think there's a difference between what we actually capture in the IR and what we display. So in this example, or if thinking out loud, right? If you had an op that was effectively so another way of representing this is effectively all of these ops do not represent an ordered output, but they're representing a map that they produce, a set. They have a set of outputs. So your type is a set. You have refined types. You could lower it down to. Your operations themselves are actually like sort of like a two-step. One is indexing into the set or extracting out, and then using it, right? And so like from the in-memory point of view, or the typeset point of view, or the type point of view in MLIR, it is still simple. With respect to the textual format, you can add some sugar to make it look similar to this, because the big difference now is that you're not producing multiple results. You're producing a set actually, and the set has a subtype effectively, and then it's a textual format thing, right? So the in-memory is still what we have in MLIR. It's to Jeff's point, it's still pretty direct. It is sugar on how people look at it. You can retain it. It's easy because you have your attributes. Some of the work, for example, Mehdi has done with like the TFG dialect, and even the executor TensorFlow executor dialect sort of like shows a little bit of these, where the in-memory format and the printed format, you can have a much more friendly printed format.
Could you do something like abstract away the parameter indexing? Like if you have like a type that indexes into a parameter by its position, and then when you're going to print that type or that operation, that automatically disappears and becomes a reference to the actual parameter that I'm referring to, like its name, something like that.
So I think the nicest way to do that is actually to do a small wrapper around some of these, because that allows you, for when you go further down and lowering, to do the easier fusion. But I think even if you go to a higher level, I mean, it's just making your print effectively more expensive, because you have to traverse, and it won't work for the built-in ops, obviously, because this is changing the print, not of the edge or the value, but of the operation, right? But so within the data flow dialect, you can do it and it can look exactly the way you would expect it to look. But once you lower down, you will lose that because it's not, you will have to effectively do the unpacking and whatnot. Once you go down to like a RIF or a CF, then it's just plain. So it's not captured, it's not captured along the value. But you can have the representation at the high level to see until you lower down.
Yeah, the way you can do that is sum up here has an array attribute of strings, and then the op ASM printer interface for the result names just like pulls strings off of the attribute and puts them out as the SSA name. So you can actually get, %1.a, %1.b, and then you do a little bit of playing with the custom parser for the op. You can make it print, .a equals or .a colon I32 and so on. So you can make that happen. But generic transformations that don't care about attributes, it's the responsibility of the operation or dialect to make sure that these get preserved.
Okay. Yeah, and another thing that another thing would be like, if we accept that an actor is an operation and we're using the inputs and outputs as their input ports and output ports, we need to be able and if you have some kind of special signature, for instance, if you have for instance, when we're talking about a data rate that depends on another port, and that's what happened with Lustre, right? They needed to add the outputs as parameters, as input parameters, to be able to do parameter indexing like that. And that suddenly changes the shape of the operation, right? Now the outputs are inputs, and it's not as easy to write to reuse pattern matching that expects some kind of flow, right? Some kind of tries to match into a directed graph that would have this expected format, right? I don't know if I'm being clear here.
Yeah, I think this is a very interesting discussion. Unfortunately, I think we're out of time for today, but I'd love this to actually continue on like I always get these two confused. Discourse.
Okay.
Yeah.
So last question. Do you think this is worth opening an RFC at Discourse? And maybe
so I think let's actually try with the like the syntactic sugar idea, just because I think that let's to Jeff's point about like the different like the different consumers of this, etc. And then we can follow up on this because I think it's sort of like proving that out first will give us an indication of like the representational capabilities, the need, etc. And I think then we can proceed from there to sort of like discuss alternatives here. Okay.
All right. Well, thank you very much. This has been very illuminating. Again, thanks for the invitation. It was Mehdi who invited me, but I thank you in his place.
Yeah, no, I'm standing Mehdi, so I'll relay. But thank you very much for the presentation, for getting all of this together, and looking forward to sort of like the discussion on this further. And thanks everybody for joining, and and we'll hopefully have one of these, I think, next week. I'm not sure.
Okay. Well, until then. Bye bye, everyone.